A little kind of housekeeping, I guess we'll call this. We have 3 more functions that I want to add to our list of things we can differentiate. And they are the inverse sine, the inverse cosine, and the inverse tangent function. And you know what those functions are from trig. Sometimes, it's not often, but then sometimes you take the inverse sine a half and find out what angle is a sine of a half, that kind of thing. So the inverse sine function does exist. And what might surprise you is its derivative have got nothing to do with sines, cosines, or even inverse sines or inverse cosines. So the derivative of the inverse sine is this ugly fraction. The derivative of the inverse cosine is the negative of this ugly fraction. Oh, have you noticed it follows the rule if it starts with a c, it's negative? Because they are very similar. And then the inverse tan doesn't even look like those two. And that's basically it. So there are going to be some formulas, some functions that have inverse sine, cosine, or tan. There is 3 others, but I'm not even going to do them, which is inverse secant, inverse cosecant, and inverse cotangent. Right, that makes up the whole 6. And if you're interested in those, you can certainly look them up. Here are the guys that we have, but they're also called arcsine, arccosine, and arctan. So you see a homework question that says arcsine of x, or arccosine of x, or arctan of x. They mean these guys. I hate that description. It is archaic. As far as I know, nobody in the world except America even does them anymore. So I'm going to stick to calling them this because I like that terminology. So let's jump right in. I got a list of questions. We're going to get practice at differentiation. These guys are essentially going to use the chain rule. This is going to be a product rule. This will be a chain rule inside another chain rule, kind of interesting. This here is a chain rule, and this here is a chain rule, product rule, and this one's a quotient rule. So I went zoom through those. If you look at an expression, you have to know before you start, what are the rules? Am I going to use a quotient rule? Am I going to use a chain rule and a quotient rule? Whatever it might be, you got to know what they are. And when you look at them, I guess through experience, you get to see it. But I'm going to start with that one, which is a chain rule. So here is the original function that we're going to find its derivative. And when you have a chain rule, you identify the inside function. So in this case, it's 4x plus 1. And I'm going to use this fella. So the derivative. Well, if you differentiate an inverse cosine, you get this thing. You get negative 1 over the square root of 1 take away the inside function squared. So it's not 1 minus x squared, it's 1 minus that guy squared. And then you always finish with the derivative of the inside function, which in this case is 4. So I have negative 4 on the top. And I have all this stuff. And it's 6 of one, half of the other, whether I can make that look pretty, but I'm going to try. If you multiply this out, you get that guy, you get that guy, and you get that guy. And there is a tiny bit of cancel. If I pull out negative x as a common factor, I get 16x. Well, actually, if I pull out, now see it, if I pull out negative 8x as a common factor, let's do that again. So if you cancel the ones out, you get that. And then factor the heck out of it. So I'm pulling out -8 as a common factor with an x, and that leaves me with 2x plus 1. And that funny looking x is still an x. And that's it. So you use, in that particular question at least, you'd use a chain rule. Now, if you wanted to do, say, the inverse tan of that guy, it's also a chain rule. And the square of x is going to be my inside function. So its derivative will be 1 over 1 plus that guy squared, followed by the derivative of the square root of x. So I've got a little side job. I need to differentiate the square root of x, I'll call it that. Its derivative is multiplied by the power, reduce it by 1. And then if you make it look pretty, it looks like that. So you get times that guy. And make it look pretty. 2 square root of x's, and that becomes an x. And we're finished. What's that, 3-liner? Not too much work. You want to differentiate that guy. Going to use this fella. Again, it's a chain rule. There's your inside function. So it's going to be 1 over the square root of 1 take away the inside function squared times the derivative of the inside function. And I'm doing a little bit of cutting corners here. If you FOIL that all out and then subtract it from 1, the 1's cancel, and you'll be left with a -4x squared, a -4x. If you pull out this time just a 4x as a common factor, you'll be left with -x, -1. You can pull out a square root of 4, which gets you 2. And those cancel down. So here's your final answer. What I'm mostly doing here is factoring the heck out of it. Step 2, right? They tend to look, you can't really say they look like the original, because with degree somewhere, a square root doesn't look like that. So rule 1 kind of doesn't matter, right? It's not going to be important. But rule 2, which is factors the heck out of it, does. Are we good? Just applications of things that we already have done, just in a context that we might not have seen so much. So let's do a product rule. Well, I know that's going to be F, and I know that's going to be G. So if I want to differentiate it, it's going to be F dash G plus F of G dashed. Right, if you differentiate an inverse tan, you get this guy. And you leave the other guy alone. And then you leave this guy alone. And you differentiate that. And really, there's nothing that I can do that's going to make this actually nice, right? There's no obvious way of putting it together. I guess I could try and add the 2 fractions. I'm not sure that would be of much use. So that one's finished. I just thought of an example. I just thought of that. I think this might be an interesting answer. Because, you know, if you do inverse sines and the original function and you put them together, and don't they tend to either cancel each other out or at least interact in a very interesting way? I think this one might interact in a very interesting way. So that guy there is my inside function. So its derivative is 1 over the square root of 1 take away that guy squared times the derivative of that guy, who is negative sine x. Right. Can anybody tell me what identity, what is that equal to?
Square root of sine x.
So 1 minus cos squared x is sine squared x. Yeah. And the square root of sine squared x is sine x. And the answer ends up being -1. That is weird, isn't it? That the derivative of this function is the number -1. Let's continue back to kind of my original list, which is this one. So next fella we're going to do is e to the inverse sine of x cubed. And yes, this is a chain rule, but this is a Russian doll chain rule. This is going to be a chain rule inside another chain rule. So the inside function is all of that. So if I want to differentiate this fella, it's going to be e to all of that times the derivative of the inside function. I don't normally write that down unless it's complicated, which this one is. Which means I now have to find the derivative of this fella. Well, this fella is also going to be a chain rule. And you differentiate an inverse sine of somebody, you get 1 over the square root of 1, take away that guy squared, times the derivative of that guy. And so this is me just making it look pretty. And that becomes x to the 6. And that's it. Can't do any more. That's as good as that expression's ever going to look, I think. Any questions? I know I'm going through these relatively quickly, but it's really just, I know what the derivative is. For the most part, it's been chain rules, hasn't it? For the most part. Right, we have a couple more guys. That guy is a chain rule inside a chain rule, so that's a Russian doll. That's going to be a chain rule, and that's going to be a separate product rule. And this is going to be a quotient rule. So that's what we've got left to do. Each one's going to have its own little idiosyncrasies that we need to deal with. Okay, I know that this is a chain rule, and I know that guy is going to be the inside function. So I know that I'm going to have to finish with times the derivative of that guy. And since I know that that's going to happen, I might as well just do a little job at the side. Let's find out what the derivative of this thing is. Well, if I'm going to differentiate it, I'm going to have to rewrite it like that. And I then identify that there's going to be a chain rule process happening. So the derivative of that is 1, -1/2 1 plus x squared to the negative a half times the derivative of that guy, which is 2x. The 2.5 cancel out. I'm going to have a x and this guy on the bottom. Are we good so far? That if you differentiate this, you get 1. If you differentiate this ugly square root, eventually you get this guy. And I am now going to do one more step. Are you comfortable about how this became that? Basically, I'm writing 1 as the square root of 1 plus x squared over itself. That way, I've now got a complete fraction. That's the derivative that we need. So, back here. It's 2 inverse tan of this guy. So it's 2 over 1 plus this guy squared times the derivative of this guy, which we just found out a moment ago was the square root of 1 plus x squared minus x all over the square root of 1 plus x squared. I can't see anything that I can do to make this look pretty. I mean, I could square that out. I don't think there's any benefit to it, so I'm not going to bother. So I guess that's just an example of an ugly question where you can't really do much. I don't see any factoring the heck out of that going anywhere. In fact, I'm not even sure I can see any factors that I could factor. Yeah, kind of disappointing, that one. I was hoping it would turn out some nicely. Well, just 2 more of these to do. I know I'm going to differentiate that. So I'm just going to rewrite it in a format that's going to help me to do that. This is going to be a product rule. And this guy's just going to be a chain rule. So multiply by the power, reduce the power by 1, and then finish it with the derivative of the inside function. So that's that piece. This here, yeah, that negative is always going to cause trouble. Okay, negative, and then just do a product rule where everybody is positive. That guy leaves me with negative x. This guy goes in the bottom. This is going to be 1 times an inverse x plus an x times a negative 1 over the square of 1 minus x squared. Ooh, that's interesting. So I have a negative x over a square root of 1 minus x squared. Negative of this guy just becomes negative inverse cosine x. The negative of this guy with the times x becomes plus x over the square root of 1 minus x squared. And that guy kills that guy off. You weren't expecting that, were you? Kind of pretty. Okay, last question. Y is an inverse sine plus an inverse cosine all over x. Pretty clearly it's going to be a quotient rule or a fraction. Here the top's going to be f, the bottom's going to be the g. Okay, if you differentiate the top, this guy and that guy, you get inverse sine has that derivative, the inverse cosine has that derivative, times the untouched bottom. Take away, do nothing to the top, leave it alone, times the derivative of x, which is 1, all over x squared. Those two guys kill each other off, so that term's 0. I've got negative 1 times this, so basically I have got negative 1 gives me that, all over x squared. We are finished with inverse trig functions. We've kind of zoomed through, actually 9 because I added one in of this type. Any questions before we move on to a totally new topic? So if you look at these questions, can you look at that one and say quotient rule? Can you look at this one and say it's definitely a chain rule of some sort? That's a chain rule, but that's a product rule. Right. If you can identify, that's a good start. Okay. Let's move on. We have finished every function that we need to know to differentiate, right? We've also finished with all the techniques. So we've done power rule, product rule, quotient rule, chain rule, implicit differentiation, logarithmic differentiation. We also know how to differentiate log functions, exponential functions, trig functions, inverse trig functions. And you put all those different techniques with all those different functions, and you've got a huge, huge list of things that can now differentiate. So what we're going to be doing now, kind of the new theme, is we're going to find uses for derivatives. Well, let's give you some uses that you already know about. You can use, I'll call it derivatives, to find the following things. Haven't we used derivatives to find the equation of tangent lines? Right. It's one of its uses. In fact, almost every question that we do, wasn't there a find the equation of the tangent line tagged on at the bottom? I could have done one with the inverse sine, cosine, but I never chose to. Right. B. Haven't we done questions where we found the value of x where the tangent line was horizontal? Didn't that basically end up being, we can find places in the curve where there's hills and valleys? Right? We've used it to do that. Haven't we used derivatives to find velocity and acceleration. So what's this section going to deal with? Well, it's going to deal with some old friends, finding velocities and accelerations again. And we're going to do a little bit of velocity curves generating acceleration curves. And we've kind of done that, not called it that, but we've kind of covered that. And then we're going to move on to finding what is typically called the rate of change. So if you've got any formula, any function in the world, and you want to find out how does it change as the variable x changes, we call that the rate of change. And the rate of change is really synonymous with derivative. So let's show you the first bunch of questions. And I'll nip over here, and I'm going to be a physics teacher, which is scary because it's not my thing, as you'll almost definitely figure out quite quickly. But the guy that you're looking at right now, and I wish they hadn't called it y, I wish they'd called it v, but it's a velocity time curve, right? So what that's telling you is that this is an object moving, and at any given time, this is its velocity. So for instance, at the 1 second mark, its velocity is 3 meters a second. At the 1, 2, 3, 4, at the 5 second mark, its velocity is 0. At the 7 second mark, it's 0. At the 8 second mark is -3. So what this graph is telling you is how the velocity of this moving object is changing through time. Right? So if you've done a physics class, you've probably seen one of them, right? A velocity time. Okay. So I'm going to do some sneaky things with it. This is my version of that same diagram. So I'm going to call that time, and I'm going to call that velocity, because to me, that's what you should have called it in the first place. And it went to there. And then for 2 seconds, it went there. So this is 1 second, 2 seconds, 3 seconds. And then in the next 2 seconds, it went down here. Should plan ahead, shouldn't you? There you go. Sec 7 seconds, it went like that. And then 1, 2, 3. For the last second, it went down like that, right? Can you pretend that's a nice, neat version of the picture we just saw a minute ago, right? Now, from this graph, you can answer various questions, but the one that we're going to start off with is we are going to create an acceleration time graph. Now, if you know the velocity and you want to get the acceleration, isn't the acceleration graph just the derivative of this graph? So we have done that process before. Remember taking a function and drawing its derivative? Right, I want you to imagine that's your f, and this is going to be our f dashed. So the first thing that I would do is I would identify, in straight line questions at least, identify the corners, because they're important. And then you draw, going to be red, I guess, little invisible lines, construction lines. There's 1, there's 3, there's 5, there's 7, you can put in 2, 4, and 6 if you like. Guess I should finish with 8. This line is straight. Would you agree that all the points in that line have the same slope and they're all positive, and that number would be, well, 3 in this case? And then from 1 to 3 seconds, isn't the velocity 0? I should be using a different color. Green looks good. And then from 3 to 5, isn't that slope pointing down the way? You agree? And if you do a little rise over run, it's roughly about 1.5, so it's about here. And then it's 0 again. And then this last bit, it was -3, which is about here. And we have just drawn an acceleration time graph. So far, so good. So if I was asking you, when is this moving object? When was it stationary? Wouldn't you say between 1 and 3 seconds and 5 and 7? So it would be stationary from 1 to 3 seconds. And I just forget that. I was thinking position time. This is velocity time. That's different. When is this object stationary? And it's not from 1 to 3 seconds, but it is stationary.
From 5 to 7.
I think I got that, 5 to 7. Is that what you said, Matthew?
Yes.
Right. If you are looking at a velocity time graph, aren't you stationary when the velocity is 0? If you were looking at a position time graph, aren't you stationary when it's horizontal? So, to give you an example, if this was a position time graph and it went like this, wouldn't it be stationary from here to here and from here to here? It only needs to be horizontal when it's a position time. When you're dealing with a velocity time, you have to interpret the information a little bit differently. Isn't stationary means 0 velocity? So that's the only bit of the graph. Right, got that one. Now, if I was asking you, how do they do it? They ask, when is it doing a constant speed? So that is also going to be from here. So try to cover this up so it doesn't distract us. For what values of time is this object going at the same speed all the time?
1 to 3.
Agreed. And now we're going to have to argue this one. I'm going to say also 5 and 7. Would you agree that it's traveling at 0 speed, but it's a constant 0? So I would include the 5 and 7 in that case. So stationary is only 5 to 7, but a constant speed is 1 to 3 and 5 to 7. So far, so good. And now the bit that, if you're not into physics, then I guess this is going to be strange to you. We're going to talk about when this object is speeding up and when this object is slowing down. And a lot of people think that it's just acceleration. In other words, this is wrong, by the way. So I'll put it down as wrong, or lots of exclamation marks. But people think if the acceleration is positive, then it's speeding up. And that is true, but not all the time. And they think if the acceleration is negative, then it's slowing down. Now, if you had that assumption, you'd be using this graph and you would be saying, oh, it's speeding up from 0 to 1 seconds, right? And that's it. And it's slowing down from 3 to 5 seconds and 7 to 8 seconds. Because isn't that positive acceleration here and negative acceleration here and here, right? And you'd be using this wrong definition. It's a little bit more complicated than that. So here is how you do it correctly. An object is going to be speeding up in two different situations. It's going to be speeding up when the velocity and acceleration are both positive. And it's going to be slowing down oh, I forgot to add my second part. Or both negative. And it's going to be slowing down when the velocity and acceleration are different signs. Okay, let me try and prove that that is correct. So I'm going to give you some very simplistic movements and showing you what a speeding up looks like. So let's look at the velocity is positive and the acceleration is positive. Let's look at that. And according to this definition, shouldn't it be speeding up? Okay, so let's suppose I have an object and its speed is 100 meters per second and its acceleration is 10 meters per second squared. The units don't matter so much, but what's that object going to look like? Well, this is a snapshot of what's happening. It's going to be doing 100 meters per second. 1 second later, it's going to increase to 110, right? Acceleration is the rate at which velocity changes, right? So it's going to go 100, 110, 120, 130, 140. Does that look like that's getting faster and faster and faster? That's what we call speeding up, isn't it? Getting faster and faster and faster. Makes sense. Now, let's do a, oh, so that is speeding up. Let's do a velocity that's negative and an acceleration that's negative. So I'm going to start with a velocity of negative 100, and I'm going to have an acceleration of negative 10. So in the first second, you're going to be going at negative 100 meters per second. Basically, you're shooting towards the ground 100 meters a second, right? So let's think negative means down the way and positive means up the way, right? Now, when the acceleration is negative 10, that means that the new velocity now becomes negative 110, doesn't it? Negative 100, take away 10, negative 110. And then it becomes negative 120, negative 130. Isn't this object just getting faster and faster towards the ground? But isn't it still speeding up? Isn't it getting faster and faster? Okay. So if they are both positive, if they are both negative, you are looking at speeding up. Now, if you do the other combinations, can you trust me, you'll get a sequence of numbers where it slows down, right? It's going 80, then it's going to do 70, then it's going to do 60, right? So have I convinced you that that's speeding up and slowed down then? So it's a little bit more than whatever the acceleration is, right? That doesn't mean speeding up. It's the interaction of acceleration and the velocity that decides if something's speeding up. So now back to our puzzle. When is this thing speeding up? And how do we tell? Well, actually, this graph is going to help us. So I'm going to go, and on this graph, in each of these intervals, I'm just going to write down some pretty obvious. Is the thing positive or negative? So forget about zeros, they don't matter. But would you agree that in this region, the velocity is positive? Right. Now, in this region, would you also agree that the acceleration is positive? There, like that. Agreed? So from 0 to 1 seconds, speeding up. SU means speeding up, right? So I'm not speeding up in that interval. Right. In interval 2, would you agree it's positive? And that's 0, so that doesn't count. In this region, it's positive, and that's negative. Okay, what's happening if something is positive velocity and negative acceleration? One of each. Speeding up or slowing down? Right. Slowing down. SD, for sure. Now, if any of them are 0, you're neither speeding up or slowing down, right? You're either going at a constant velocity or you're not moving, right? So we don't worry about the 0 ones, right? So that's why this interval doesn't matter. And the last one, negative here and negative here. What is happening in that last interval from 7 to 8 seconds? Speeding up or slowing down? From the 7 to 8 second mark, velocity and acceleration are both negative. Speeding up, slowing down. What's happening?
Speeding up.
Speeding up. For some of you, does that seem counterintuitive? But nonetheless, it's speeding up. It's just speeding up because it's crashing towards the ground even faster, right? It's getting faster as it heads towards the ground, essentially. Are we cool with that question now? Now, I'm going to zoom over and show you the rest of that bunch of questions. Oh, I got the answers here. Oh, that's fine. We got them. Let's take them off. And there's another picture. And it asks you speeding up or slowing down. There's the graphs that you pick. One of them's right. Okay. And then it asks you speeding up and slowing down. And that's pretty much that. It's not a big group of questions, but that's that question finished. So what we're going to do now is things that we have done before. We've done questions like this. So this is a version of question 3. I don't think you can see it yet, can you? Right, this is a version of question 3. An object is chucked into the air and its height at any given time, t, is given by this ugly formula. And you're going to be asked things like, what is the velocity after 2 seconds? And then, what is the velocity after 4 seconds? So, can you imagine this is time and this is the height of the ball, and you know, it does that, right? That's kind of what it would look like, up and down. Right, if you want to get velocity, and this is the position function, don't you basically just find the derivative? And even if they're ugly numbers, it doesn't mean that you change the rules. You just have to do, you know, you have to live with the ugly numbers. So if you want to know what's the velocity of this object at the 2-second mark, it's 25.5, take away 9, and I just put a t squared there, nobody noticed. Take away a 9.8 times t, which is 2. So it's 25.5, take away 2 times 9.8, and the answer is positive 5.9, and the units are meters per second. And at the 4-second mark, it's going to be 25.5, take away 9.8 times 4. And this is negative 13.7 meters per second. So can you imagine that's roughly 2-second mark? Do you see the 5.9 means it's going up the way, right? It's still climbing upwards. 5.9 meters a second. By the 4-second mark, isn't it probably there? Can you see it's now heading towards the ground? You see velocity upwards is positive, velocity downwards is negative. So I already have a little snapshot of this object as it was thrown in the air. Right. This is how fast it's going, its velocity at the 2-second mark. This is its velocity at the 4-second mark. Now the next question is phrased like this. When does it reach its maximum height? Well, I can tell looking at my picture. Would you agree that's where it reaches its maximum height? But they want to know when it happens.
Max.
So how am I going to do it? I'll do a quick mute, so you'll have to hit the space button. How am I going to find when it reaches maximum height? How's calculus going to help me?
Wait, what was the question again?
How will calculus help me find when the velocity, I almost gave the answer, when it will reach its maximum height? Could
The
be
top of
just
the
an
arc will be 0.
Yeah, that's it.
Velocity.
Yeah. All I need to do then is solve when is the velocity 0. Agreed? Because at that point there, won't the tangent line be 0? And so if you're looking for max and mins, which sometimes you are, you're really looking for when is a derivative 0. Right, that's the calculus helping us with that. Well, it's an ugly formula, but it doesn't mean I can't solve it. I'm trying to find out when that is 0. So as long as I do it to both sides, it's okay roll. So I'll subtract 25.5 from both sides. And then I will divide both sides by negative 9.8. And they want the answer to 2 decimal places. So 25.5 divided by a 9.8 to 2 decimal places is 2.60 seconds. And then it says, what is that maximum height? Well, if I want to know what the maximum height is at 2.6 seconds, I just plug it into here to see what height it would be then. So it's a 2 plus a 25.5 times 2, take away a 4.9 times 2 squared, and you get the answer and call it whatever it is. Now, the next question that they ask is, when does it hit the ground? And I would probably put E with it. What's the velocity when it hits the ground? So my little crude picture looks like that. And we are interested in there, right? How many seconds is that? And once we figure that T out, which is going to have to be rounded off to 2 decimal places as well, then won't we just find, let's say T equals something, won't we just find the velocity at that value of T? And I'm pretty sure it would be negative when it does hit the ground. Well, technically speaking, I need to solve when is the height 0, which is when is this guy well, in some situations, not this one, couldn't I simply just factor it and solve it that way? Would you agree that's not a question that's going to factor? Another alternate would be, couldn't I use that horrible formula called the quadratic formula and solve it that way? But I'm not going to do that either. So how am I going to solve it? I'm not going to do algebra. I'm not going to use the quadratic formula. How am I going to do it? I'm going to use Desmos. Right? That makes sense? Always take the easiest road if you're given the choice. So let's do that then. Now, I'm pretty sure Desmos can handle this, so I'm going to call it H equals 2 plus 25.5 and take away 4.9 t squared. And if I shrink the window a little bit, okay. Don't like the scale, it's kind of ugly. So I'm going to change the x values and start at 0. And I think I should be able to finish about 8. There we go. There, would you say that's more what I need, right? My picture of up and down was quite wrong then, but never mind. Isn't that
Professor,
the place?
your 25.5 needs a variable.
Oh, thank you. Ah, right. I guess that does look a little bit better then. It does look up and down. Thanks for catching that. Right, now, the guy I'm interested in is right here, right, hitting the ground. How about 5.28? Does that look good to you? So we found the answer. When does it hit the ground? 5.28 to 2 decimal places. So I'm going to kick out of this again. And E was, what's the velocity? Well, if you want to do the velocity then, and we just take, where is our friend? Take this guy and we evaluate it at 5.28. So it's going to be 25.5 take away 9.8 times 5.28, and you get whatever ugly answer it happens to be. Are we okay with that? So if you tell me the position of an object, right, the height of an object or its position, don't matter, can I find velocity and acceleration by calculus? Can't I also use it to find velocity at 2 seconds, 10 seconds? I can use it to find the velocity. Well, I can use to find when it reaches its highest, its maximum height or its minimum height. I can even tell you what velocity is when it hits the ground. And all of that came from only knowing the position of the object at any given time. Which is pretty amazing, I think. And question 4 is very similar. So we have done velocities and accelerations before. So it's those guys covered. Now the new guys. If you tell me any formula from anything in business, in physics, chemistry, any science at all, I would almost guarantee that in most cases, you're going to be interested in the rate of change of that thing. So let's do one that we know. If I tell you the position of something is that, then if you find its rate of change, if you find its derivative, in other words, in this case, don't you get a guy called the velocity? If you take a formula for the velocity of something, and you find its rate of change, its derivative, you get a thing called the acceleration. Suppose I tell you the volume at any given time t. So let's have a tank, right? I get a tank of water, and it's got a leak, and it's shooting out of that tank. And I tell you that the volume is given by that formula there. So the volume is given by this formula. What I'm going to do now is find the rate of change of that volume. So what the rate of change is telling me is how the volume is changing through time, right? So what's the volume at 1 second? What's it going to be like in 2 seconds from now? What's the volume going to be like in 5 seconds? Can you see that this tank is going to have less and less and less volume of liquid, isn't it? Because it's shooting out. So if you find the rate of change of this guy, it's going to be called that. And the rate of change will tell me what's happening at any given moment of time to the volume of this tank. Now, if I'm going to differentiate this guy, oops, it's going to be, well, I guess I was going to FOIL it out, but I've changed my mind. Couldn't I do this as just a rather ugly chain rule? So multiply by the power, reduce the power by 1, and then finish with the derivative of the inside function. Okay, if you want to differentiate that guy, you probably should call it that guy, agreed? And so when you differentiate it, you're going to get plus, I guess I shouldn't need that, 5v to the negative 2. So it's going to be 200, 1 take away 5 over v, all over v squared. So I now know what the rate at which the volume of that tank, what volume it's going to be. It's going to be given by this calculation. So if you wanted to, for instance, know what the volume is at the 1 second mark, right? Then the rate of change at the 1 second mark is 200, 1 take away 5 over 1, all over 1 squared, which is 200 times -4, -800, whatever the units are, cubic meters per second. Can you see that the water is going to be shooting out that tank at a really high amount? And it's negative because isn't the volume decreasing because there's a hole in it. So all you need to do is tell me what this guy is, and I can find its rate of change, its derivative, and that could tell me something important. So imagine we've got an oil slick. And my oil slick is going to be modeled by a circle. Do you know if you put oil in it, it makes a little kind of sort of a circle, but as the oil increases, does it the circle get bigger, right? And let's say that the area of that circle at time t is given by pi t squared. Then what is the rate at which the area of that circle is changing through time? The answer is 2 pi t, its derivative. And if I wanted to know at what rate, say, at the 2-second mark, the answer would be 2 pi times 2. It would be 4 pi, and then you can put in whatever the units happen to be. So I can tell you that if you imagine this oil slick, right, this big circle of oil, at the 2-second mark, it's going to grow from here to here. And that increase in area is that number, right? It's just telling you how much it's increasing by, right? So at that point in time, it's going to be increasing at roughly about 12 square meters a second. So you can imagine how quickly that circle's growing. So the moral of the story is just tell me what the formula is, and we will differentiate it, and we can find out the rate at which that thing is changing, and typically through time. So this one is a version of a homework question. A company that makes computer chips, square ones, in fact. And the process engineer wants to keep the length of the side of the wafer very close to 20 millimeters, and he needs to know how the area of that thing, area of X, changes when the side length X changes. Okay. If you're making square chips, won't this be X by X? And so won't the area be X squared? So that question sounded like it was a lot harder than it was, right? I just need to create the formula for the area of a square chip of side X. Now I want to find the rate at which the area is increasing. So if you make a little extra bit onto that, right, you'll get a bigger square, won't you? How much will it increase by? It will be 2x. And what's the area going to be when it's at 20 millimeters? The increase in area is going to be 40 square millimeters. So a little adjustment, right? So if this was 20 millimeters and it grew just a little bit bigger, that's how much it would grow at that size. Let me show you a cool little thing. Side issue. You all recognize that guy? Area of a circle. I wonder what the rate of change for the area of a circle is. Do you recognize that? What does 2 pi r typically get you? What's
One
it
rot-
calculate? Robert?
I was going to say 1 rotation around the circle.
It's the circumference.
Hmm.
Right? Now, if you want to imagine what that looks like, here is a circle whose radiuses are. If you increase that circle by a little, which is what the rate of change is telling you, what would happen to the increased area? Wouldn't the circle increase by roughly a circumference worth, right, of area? This one's less obvious, but maybe you know it. I hope you do. Does anybody know what that formula is? What does that calculate?
Area of sphere.
Close, definitely to do with a sphere, not the area.
Then volume.
Yes. So that's the volume of the sphere. I'm now going to do its derivative, right? Multiply by the power, and we get this guy. Does anybody know what that formula is? That'd be really cool if you knew it. So can you imagine a sphere growing a little bit? Wouldn't a sphere grow by the surface area of its shell? So rate of change is telling you how a shape will grow in an instant in time. You know, like a micron worth would be basically, wouldn't it be like the skin of an orange, right? Well, that's the surface area, right? The outside surface. Try to think of one. Has anybody seen this one? Do you recognize that formula? It may not be, you may have a little U naught in it or something. Anybody did mechanics? Do you recognize that formula?
Is that force?
No.
Gravity?
It does have gravity connected to it and acceleration. That's the velocity of an object with an instant initial velocity of u and acceleration of v. This is the formula for the velocity. How about this one then? Anybody seen that one? Right, it's the position of an object at t seconds with acceleration of a and a unit, an initial velocity of u naught. If you differentiate any of these guys, you will end up with another formula that you've seen in physics, right? Anybody seen that one? It's my last one. E equals a half mv squared. If you find it's the kinetic energy of a moving object. If you differentiate it, you get mv, which is the momentum of a moving object. What I am not very successfully doing is trying to tell you that any formula that you've ever seen in physics, chemistry, or science, if you differentiate it, you've probably got another guy that you use in physics, chemistry, or science. Okay, let's return back to their questions. In question 6, they have a cube. Well, the volume of a cube, if you don't know its side, is going to be called x cubed.
So, Professor,
Yes.
Whenever looking at the differentiation of those formulas, is it increases the different, like for volume, it increases the difference of the surface areas of the two, and it's the shortcut, like we don't have to find each and subtract. Is that basically
Yes.
what we were looking at?
Yeah, it's a way of figuring out what would happen without having to do the before volume, the after volume, subtracting them and dividing by time.
Multiple calculations.
Yes.
Okay, thank you.
Does that sound like you've done something like that before, but not doing it with calculus?
Oh, yes. Surface area is excruciating to teach.
Oh,
It's
okay.
long. I would rather do volume. I would rather do anything than surface area.
I hear you. Okay, so v equals x cubed is the start, and we want to know the rate of change at the 5-second mark. Well, if you want to find the derivative, I guess I should call it v of x, it's just going to be 3x squared. And so the rate of change at the 5-second mark is just going to be that. And the units in this case happen to be cubic millimeters per millimeter. They give you that. You only type in that. So the questions, for the most part at least, are if you give me a formula, can I find the derivative which will tell me the rate of change? And won't I probably then evaluate it at some given value, in this case 5, or in this case 2? Any questions? Right. I'm jumping ahead to question 10 now. Is it 10? No, my apologies. It's 11. And the quantity of charge at any given time t in a circuit is given by t cubed take away 4t squared plus 6t plus 4. And they ask me to find the current at t equals 0.3, and then at t equals 1, and then after that they ask me for the lowest current. This is the charge in this circuit at any given time t, and it's changing. So obviously there's charge going in or coming out, hard to tell which, but this is what it is. And they're asking us for the current. Well, the current is the rate of change of the charge. Now, if I didn't know that, I will work on the principle that when I'm in this question and they give me a function, won't I differentiate this function? Because that's kind of what you're going to do, right? So I now know what the current is. The current at any given time t is the derivative of this guy. So it's going to be 3t squared take away 8t plus 6. And I guess I'll call it C of t, right? The current. Now you want to know the current at point 3. It's 3 lots of 0.3 squared take away 8 lots of 0.3 plus 6. And if you want the current at the 1 second mark, which is what I'm going to do, it's 3 times 1 squared take away 8 times 1 plus 6, and I believe that is 1, and the units happen to be amps. So the question is, at what time do you get the lowest current? Well, the current is 3t squared take away 8t plus 6. And I'm going to make an assumption here, which better be true or I'm in trouble. Would you agree that the lowest current you can get is no current at all? No one has invented negative current yet. Please, nobody invent negative current. That's just going to screw this up. So I'm basically trying to solve this, aren't I? And, oh, I could factor it, couldn't I? What other choices have I got? Quadratic formula. And last but not least, Desmos.
Yes.
So let's do Desmos. Because I don't think that factors, but if it does, that's fine. So according to Desmos, then C, the current, is equal to 3t squared take away 8t and add a 6. And I have just noticed something that's kind of cool. I went and said the lowest current is 0. Shouldn't I have just said the lowest point in the curve? Because you notice it's not 0. I just assumed that it was going to be 0. So I'm really glad that I did that. Now, about here. Can I move it a little here? Now, I think Desmos kind of knows what I wanted, so how about 1.33 seconds? That seem reasonable? 1.33. And that's the end of that question. So it feels a bit like a physics class, as I said, or engineer class or something. But as far as math is concerned, don't you basically just differentiate the thing and plug in numbers, or differentiate the thing and find out when it's smallest or biggest or 0? That has made physics and a lot of sciences a lot simpler, at least if you're good at calculus. Last one for today. The depth of tide at any given time t is given by this really ugly formula. And although it's really ugly, in a lot of ways isn't really ugly, also really realistic. Because in real science, you don't get 2t squared plus 4. Don't you get ugly number of t squareds and all sorts of footy decimals. And we are being asked to find how fast the tide is rising. Or falling, I guess. Well, won't that just mean find the derivative? Right? If you want to find the rate at which something is changing, right? How fast it's going, how slow it's going, how's it changing? Find the derivative. Now, the only nice bit about this is that the 7 gets you 0. This is 5 cosines of ugly guy. So it's a chain rule. This is the inside function. If you differentiate 5 cosines, you'll get negative 5 sines of this fella. Times the derivative of the inside function. Now, if I multiplied that out, would you agree that all you've got is 0.503t? And so when you differentiate that, you just get 0.503. And so I am now going to have to do a little multiplication by 5. So 0.503 times 5 gets me negative 2.515, the sine of this ugly calculation. And this will tell me the rate at which the tide is rising or falling. And they want to know what's happening at 2 a.m. Well, that's just going to be negative 2515, the sine of this guy at 2. So it's 2 takeaway 6.75. And here goes negative 2.515 times the sine of 0.503 times a bracket 2 takeaway 6.75. Close the couple of brackets. Hopefully that's the right number. And the answer is 1.72, and the units are meters per hour. So if you were in this particular harbour and it was 2 a.m. in the morning, the tide would be rising at the rate of 1.72 meters per hour. So that gives you an idea of how quickly, you know, the tide is going. Now, if that number was a negative, wouldn't that just be, it would be going down the way, right? The tide's going in, the tide's going out, right? Plus it's getting bigger. Negative, it just means the tide's going down. And so you can look at these and calculate any time that you like. Pretty cool. Now, if you really wanted to create one, let's suppose Illihi Docks wants to know what the tide looks like, right? The tide is pretty predictable, right? It's very closely connected to the moon. So what you could simply do is pick a 24-hour time period and plot, right, the height, right? So you've got the depth of water, right? If there was, you know, no water on the tide, and, you know, it would look probably something like this. You know, start, whatever the interval for that would be. Tell me for a moment, the tides normally do 28-hour cycle, 28-day cycles, because that's what a full moon takes, 28 days roughly. Right, anyway, if it was, that number there would be 7. This number here would be 12. This number here would be 2, so it never gets lower than 2 feet in this place. And from here to here would be 28 days. And you would just take snapshots, maybe each day at a certain time, whatever it was, and you could create that model. And there's lots of software that you can use today where all you do is plug in the numbers and tell the computer, I want you to make a formula that looks something like this, and it will find all the magic numbers for you. And boom, you can now make a prediction on how the tide is rising or falling in Illihi Dock or any other dock. And I'm pretty sure that people who need to know that, like the Navy, probably have these things already in, and they know exactly what's going to happen, right? And that is us for today. So last